For lesson 14, let's talk about organic acids. I've given you a few here. They're common, so we're going to get used to them. And I've given you the pKa values because we talked about what that means in the last lesson. The higher the number pKa, the weaker the acid, and the stronger its conjugate base. So let's look at maybe why that might be for some of these common ones. And on the left here, I've taken away the carbon and hydrogens, right? Because we're wearing our big boy or big girl pants today. And we're looking at these as actual representations of a molecule now. So methanol, meth meaning one carbon, there's a methyl group here, and there's an alcohol group here, is going to be the first acid we look at. An ethanoic acid, better known as acetic acid, I'll write it on here, has a methyl group, except it's not alone, is it? There's another carbon here. So two carbons, that's ethanoic acid. No longer is it methanoic acid. And the third one here, acetone, its real chemical name is propanone. Prop meaning three carbons here. Okay, that was a Sesame Street reference. I'm dating myself here. 3 carbons, propanone, i.e. acetone, has the weakest acidity of these three with a pKa of 19.3. So let's look at why. Let's look at why that might be. We're going to need to take a look at the conjugate base to understand it a little bit. So here's my oxygen, and now he's a minus ion because we've lost our hydrogen, and he has 3 lone pairs hanging off of here, so his formal charge of -1 is going to be due to 7 localized electrons here. And if I look at acetic acid's conjugate, well, it's going to be the same thing, isn't it? There's going to be a minus over here, and there's going to be an oxygen that's got a minus charge off the end of it due to 7 localized electrons. But oxygen is very happy to do that. That's what oxygen does best, is it holds an extra electron. Of all the elements, oxygen is one of the most electronegative. Look how small oxygen is. So if you bring an extra electron nearby, it's going to be able to hold pretty darn close to the nucleus. This is only the second energy level. And oxygen is a little bit desperate to get to a full octet. It would really like that. So aside from fluorine and maybe even a little bit chlorine, oxygen is going to be pretty electron loving. And that's exactly what allows methanol and acetic acid to be acidic. And we'll address why their pKa's are so different in a minute, but I want to come over now to acetone. Let's address acetic acid while we're here. This extra minus charge here, the extra electron somewhere in this cloud, is not localized to this oxygen. This double bond means that there are p orbitals. Maybe I'll try and draw it a little flat here. Let's say it's flat. Let's say this whole thing is flat, two-dimensional, and there's an oxygen and a carbon and this oxygen here. Their p orbitals are overlapping on this side here like this. And it allows the extra electron to participate in some kind of resonance fluxing here. So that minus charge is not localized to the edge of the oxygen like it is over here on methanol. There's only a carbon here. There's no double bond. There's no p orbital overlap here. This one has all kinds of p orbital action, but the carbon, not so much. He's just got some hydrogen sigma bonds out here. His p orbital is open and empty and unused, and it's going to stay that way. But oxygen over here, this double bond here, means that we have pi bond. And pi bond means that there is p orbital overlap with this carbon here like this. There's a big electron cloud here. This electron is absolutely close enough to participate in that cloud. So this electron is maybe let's say it's this electron here, is in the sphere of influence that allows it to, where'd that dot go? That allows it to drift between oxygen, carbon, oxygen, carbon, oxygen, and as a consequence, it's much more stable. And conjugate bases that are more stable result in stronger acids when they have the hydrogen still attached. So notice how much stronger acetic acid's pKa is compared to methanol. It is not for any reason other than that the conjugate base here can participate in this resonance. So when you see a double bond next door, just remember that. That means resonance, and resonance means stable. And a stable base means stronger conjugate acid, and vice versa. Okay, now let's come over to acetone. Let's call it propanone, since that's a better name for it. It tells us what we're looking at. Acetone being its trade name, it's not so useful. The conjugate acid has a minus on it over here. This methyl group only has 2 hydrogens attached to it now. There's no longer really a true methyl group. It's some kind of a CH2 anion, right? And isn't that interesting? This isn't an oxygen that's holding onto the minus charge, and carbon doesn't like having a minus charge as much as oxygen does. Not by any stretch of the imagination. So it might not surprise you to find out that this is a weak acid because, of course, carbon's not as electronegative as oxygen, and therefore it's not going to be as stable as something like ethanoic acid. But moreover, this weakness is on top of the fact that it's participating in resonance because, like we just said, look at this double bond here. This minus charge is delocalized from this carbon to this carbon to this oxygen. And moreover, you could have put the minus over on this side and said this structure works for us too. So you actually see that this minus is delocalized all over the place on this molecule, and it shares the load. Even this -1 charge is shared across this entire molecule. So even with all of the resonance structures we could draw, one of them being like this maybe, then these are natural, and one of them being like this with the minus over here, we can come up with other ways to imagine where the electron would want to live. And as a consequence, acetone can exist as an acid at all. Because a methyl group, let's take these away just to get them out of the way. A methyl group does not want to lose a hydrogen. You don't just see a CH3 give away its hydrogen for no reason. It has to be compelled. And even as such, it needs to have resonance with which to share the extra electron across the molecule. Otherwise, this 19.3 is going to be more like 40, and you're not going to see an acidic behavior at all. So notice something here. Methanol, where it's just an OH group, an alcohol group, is able to be a weak acid all by itself without any help. Acetone is able to be an acid because it can drop a hydrogen off of its methyl group and participate in resonance. But ethanoic acid does both. Ethanoic acid uses an alcohol and then delocalizes the electron across this molecule, and is, as such, with both of them combined, is able to act as a stronger acid. So for this lesson, what you can take away from these sort of different examples is that one group here, oxygen, with a hydrogen attached, can be an acid, and over here resonance can allow something to act as an acid, but when you combine both you have stronger acid. And in fact, this structure by itself, where you have an O that's double bonded and another O that ends up as an anion, or even if you see an OH here like this, either way, that's a carboxylic acid group. There's a name for it. And over here we could just have one carbon attached, like there's ethanoic acid. Here's a simple version, but you could have any kind of stuff over here. And after a while I could even start attaching all kinds of weird stuff. It doesn't really matter, because that is too far away from here to affect the acidity and the behavior that you're going to see. So if you have ethanoic or propanoic or butanoic or pentanoic or hexanoic acid, it doesn't matter. These carbons aren't involved in what makes this acidic. It's the resonance across these double bonds and the electronegativity of the oxygen that work together to give you a stronger acid group here. So if you see an OH group, you should be thinking that's probably an acid. And if you see a double bonded oxygen next to the tail end of something, you might be thinking weak acids. Or in the carboxylic acid case, when you see both of those, then maybe you should expect somewhat of a stronger acid. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.